Hi everyone, in this video we are going to see how to find the equations of the direct common tangents and the transverse common tangents for two disjoint circles which are located like this. They do not intersect each other and they do not touch each other. They have a little bit of distance between them. For these two circles, let's assume the equations are like this: x squared plus y squared plus 2g sub 1x plus 2f sub 1y plus c sub 1 is equal to 0. That's the equation of the first green circle, which is the larger one. And then the equation of the smaller circle is x squared plus y squared plus 2g sub 2x plus 2f sub 2y plus c sub 2 equals 0. Then the location of the centers of these two circles would be like this, and from the given equation we can say that the radii of those two circles would be like this: r sub 1 equals square root of g sub 1 squared plus f sub 1 squared minus c sub 1, and r sub 2 is equal to square root of g sub 2 squared plus f sub 2 squared minus c sub 2, where r sub 1 is the radius of the larger circle and r sub 2 is the radius of the smaller circle. And what would be the distance between P and Q, the two centers? Well, that will be like this: square root of g sub 1 minus g sub 2 whole squared plus f sub 1 minus f sub 2 whole squared. Next, I am going to do a few little constructions here. First, I am going to join the centers of the two circles and extend that line. Next, I am going to draw the first direct common tangent, and then I am going to draw the second direct common tangent, which would be on the lower side. Then I am going to draw the first transverse common tangent, and next I am going to draw the second transverse common tangent. Let's assume the direct common tangents intersect at point D, and let's assume the transverse common tangents intersect at point T. I have assumed D's coordinates to be x sub 1, y sub 1 and Th's coordinates to be x sub 2, y sub 2. From the diagram, we can clearly see that the direct common tangents intersect at a point which lies on the extended PQ line, and also we see that the transverse common tangents also intersect at a point which lies on that PQ line. So looks like P, Q, D and T, they all are collinear. I mean, of course PQ would be collinear because they are just 2 points. Now here we have to somehow prove that D and T will also lie on that PQ line or the extended PQ line. So how are you going to prove that? First, let's try to prove that the direct common tangents intersect at a point which lies on the extended PQ line. Here I have removed a few things from the diagram. Next, I am going to do a couple little constructions here. I joined P with the point of contact for the larger circle, and I joined Q with the point of contact for the smaller circle. And let's suppose the points of contact are A and B, and let's assume that the direct common tangent meets the extended PQ line at point D sub 1. They will definitely meet if the radii of the two circles are different. If the radii of the two circles are equal, then the direct common tangent and the PQ line will never meet. They will essentially be parallel. But we are taking an example here where the radii are different. So let's assume that the direct common tangent meets the PQ line at point D sub 1. We know that radius is perpendicular to the tangent. So in this case, we can say AP will be perpendicular to AD sub 1. And similarly, BQ will also be perpendicular to the direct tangent. Here we have two line segments which are perpendicular to the same line. That means these two line segments will be parallel. I mean AP and BQ, they will be parallel to each other because they both are perpendicular to the AD sub 1 line. So from here we can say that angle APD sub 1 will be equal to angle BQD sub 1. They will be corresponding angles. And also angle PAD sub 1 will be equal to 90 degree because we know radius is always perpendicular to the tangent. And similarly angle QBD sub 1, that will also be 90 degree. So now if you look at these two triangles, triangle APD sub 1 and triangle BQD sub 1, if you look at these two triangles, you will see that they have corresponding angles are all equal, and of course they have a common angle there, right? So angle PAD sub 1 is equal to 90 degree, and similarly angle QBD sub 1, that is also 90 degree. And then we have proved that angle APD sub 1 is also equal to angle BQD sub 1 because they are the two corresponding angles between two parallel lines, and the angle BD sub 1Q, that angle is a common angle between both the triangles. So then we can say that the two triangles are similar triangles. triangle APD sub 1 and triangle BQD sub 1, they are similar triangles. And because they are similar triangles, we can say that the ratio of the corresponding sides would be equal. Now let's take the first part of the proportion here, and from there we can say that PD sub 1 over QD sub 1 will be equal to AP over BQ. Now what is AP? Well, AP is actually R sub 1 and BQ is actually R sub 2. So we can say that that will be equal to R sub 1 over R sub 2, and from there we can say that PD sub 1 is to QD sub 1 is equal to R sub 1 is to R sub 2. That means the point D sub 1 divides the PQ line segment externally in a ratio of R sub 1 is to R sub 2. So far we see that the D sub 1 point is actually dividing just the PQ line segment externally in a ratio of R sub 1 is to R sub 2. Next, we are going to look at the second direct tangent and see how that behaves. For the second direct tangent, I have done similar construction here. Let's assume that the points of contact are E and F. And also let's assume that the second direct tangent intersects the extended PQ line at point D sub 2. We are simply assuming that the direct tangents, they intersect the PQ line at two different points, but finally we will be able to prove that actually it's the same point. So previously I assumed the point was D sub 1, and here I am assuming that point is D sub 2, and finally we will be able to prove that D sub 1 and D sub 2, they are actually coincident. I mean, they will be the exact same point. So now let's proceed with our proof. So here again PE is perpendicular on ED sub 2, and similarly QF is also perpendicular on FD sub 2, because we know that radius is perpendicular to the tangent. So from here we can say that PE is parallel to QF, and then we can say that angle EPD sub 2 will be equal to the angle FQD sub 2. Those will be the corresponding angles between two parallel lines. And also we know that PED sub 2 is a 90-degree angle because radius is always perpendicular to the tangent. And similarly angle QFD sub 2, that is also a 90-degree angle. And here again, if you look at these two triangles, the triangle PED sub 2 and QFD sub 2, you will see that they have corresponding angles are all equal. They have one common angle, which is the angle FD sub 2Q, that is common between both the triangles. And then angle PED sub 2 and angle QFD sub 2, they are 90-degree angles, and also angle EPD sub 2 and FQD sub 2, they are equal angles. So we have two triangles here, the larger one and the smaller one. Both triangles have corresponding angles equal. That means these two triangles are actually similar triangles. And if they are similar triangles, then the ratio of their corresponding sides will be equal. And if we take the first part of the proportion here, we can say that PD sub 2 over QD sub 2 will be equal to PE over QF. Now what is PE? Well, PE is actually R sub 1 and QF is actually R sub 2. So this quantity can be written as R sub 1 over R sub 2. So from here we can say that the ratio of PD sub 2 to QD sub 2 is equal to R sub 1 is to R sub 2. That means here again we see that D sub 2 externally divides the line segment PQ in a ratio of R sub 1 is to R sub 2. Previously we saw that D sub 1 divided the same line segment, which is the PQ line segment, externally in a ratio of R sub 1 is to R sub 2, and here again we see that the point D sub 2 also dividing the same line segment externally, of course, dividing the same line segment in a ratio of R sub 1 is to R sub 2. So evidently D sub 1 must be coincident with D sub 2 because it's a point on that extended PQ line which is externally dividing the PQ line segment in the same ratio. So we cannot have two different points dividing a line segment in the same ratio. If a point has to divide a line segment in a particular ratio, that point has to be just a single point. We cannot have two different points on the extended PQ line that will divide externally the PQ line segment in two different ratios. So we can say that D sub 1 and D sub 2, they must be the same point. They must be coincident. So now we are able to prove that we have a single point on the extended PQ line where the two direct common tangents intersect each other, and that intersection point actually lies on the PQ line because that point divides the PQ line segment in a particular ratio, and that ratio is the ratio of the two radii. Next we are going to see how we can prove that the intersection of the two transverse common tangents will also lie on the PQ line segment. Here I have removed the direct common tangents and I have drawn one of the transverse common tangents, and also let's assume that the points of contact are K and L, and I have joined the centers with the points of contact. And let's assume that this transverse common tangent intersects the PQ line segment at point T sub 1. From the diagram, we can clearly see that PK will be perpendicular to KL because radius is always perpendicular to the tangent. And similarly, QL will also be perpendicular to KL. That means PK and QL, they will be parallel to each other. And from there, we can say that angle KPT sub 1 will be equal to LQT sub 1. There will be the alternate angles between two parallel lines. And also, angle PKT sub 1 will be equal to 90 degree. And similarly, angle QLT sub 1, that will also be equal to 90 degree. And also, if you think about the vertically opposite angles, which are actually angle PT sub 1K and Q T sub 1L, those two angles are vertically opposite angles. So here we have two triangles PK T sub 1 and triangle QL T sub 1. These two triangles have corresponding angles as equal. That means those two triangles are similar triangles. And because they are similar triangles, the ratio of their corresponding sides would be equal. And taking the first proportion, we can write it like this. We can say that PT sub 1 over QT sub 1 will be equal to R sub 1 over R sub 2. And that can be written as PT sub 1 is to QT sub 1 is equal to R sub 1 is to R sub 2, which means that the point T sub 1 internally divides the PQ line segment in a ratio of R sub 1 is to R sub 2. So here we have a point which is T sub 1 that divides the PQ line segment in this ratio, which is R sub 1 is to R sub 2. And next we are going to look at the other transverse common tangent, and we are going to find that there will also have a similar point which will divide the PQ line segment in the exact same ratio. So let's take a look at that. So here I have taken the other transverse common tangent, and let's assume that the points of contact are M and N, and also let's assume that this tangent intersects the PQ line segment at point T sub 2. So here again we can say that PM will be perpendicular to MN because we know radius is always perpendicular to the tangent. And similarly, QN will also be perpendicular to MN. That means PM and QN are parallel. That means angle MPT sub 2 will be equal to angle NQT sub 2. Those will be the alternate angles between two parallel lines. And also angle PMT sub 2 is equal to 90 degree. And similarly, angle QNT sub 2 is also equal to 90 degree. And if you look at the vertically opposite angles, which are angle PT sub 2M and angle QT sub 2N, they are also equal angles. So now if you look at these two triangles, triangle PMT sub 2 and triangle QNT sub 2, you will see that their corresponding angles are all equal. That means those two triangles are also similar triangles. And because they are similar triangles, the ratio of their sides will be equal. And taking the first part of the proportion, we can say that PT sub 2 over QT sub 2 will be equal to R sub 1 over R sub 2 because PM is equal to R sub 1 and QN is equal to R sub 2. So this can be written as PT sub 2 is to QT sub 2 is equal to R sub 1 is to R sub 2. And that means the point T sub 2 internally divides the PQ line segment in a ratio of R sub 1 is to R sub 2. So here again we see that we find another point which is T sub 2 that also divides the PQ line segment internally in a ratio of R sub 1 is to R sub 2. And previously we found that there was another point which is T sub 1 that also divided the same line segment, the PQ line segment, internally in the same ratio R sub 1 is to R sub 2. So now we are talking about two points which are T sub 1 and T sub 2, but they both divide the same line segment internally in the same ratio. That means both points have to be coincident. They cannot be two different points. They have to be the exact same point. So from here we can say that T sub 1 and T sub 2, they are actually the same point. So we can see that the transverse common tangents intersect at a point which lies on the PQ line, and also the direct common tangents intersect at a point which also lies on the PQ line. I hope things are clear up to this point. Next, we are going to try and calculate the length of AB, the common tangent portion there. Here I have drawn a line parallel to PQ from the point B onto the PA line, and let's assume that line is BH. So HB is parallel to PQ and PH is also parallel to QB, because you know PA is parallel to QB, that we have seen before, because both of them are radii and they are perpendicular to their common tangent. So PH will be parallel to QB. Now if we look at this quadrilateral PQBH, this will be a parallelogram because we have opposite sides are parallel to each other. So from here we can say then HB will be equal to PQ. And what is PH? Well, PH and QB, they are equal to R sub 2. So from here we can say that AH will be equal to AP minus HP, that can be written as R sub 1 minus R sub 2. Again, R sub 1 is the radius of the larger circle and R sub 2 is the radius of the smaller circle. Now in the little triangle ABH, if we use Pythagoras theorem, we can say that AB squared plus AH squared is equal to HB squared. And from there we can say that AB squared is equal to HB squared minus AH squared, and in place of HB we can write PQ because HB and PQ they are equal. So we can write it as PQ squared minus AH squared, which is nothing but R sub 1 minus R sub 2 whole squared. And from there we can say then AB length will be equal to the positive value of the square root of PQ squared minus R sub 1 minus R sub 2 whole squared. And what is PQ squared? Well, we have already calculated the value of PQ. PQ is equal to square root of G sub 1 minus G sub 2 whole squared plus F sub 1 minus F sub 2 whole squared. So we can easily calculate the value of PQ squared, and then R sub 1 and R sub 2, they are also known quantity. Everything is known from the two given equations of the circles. So we can easily calculate the length of the AB line segment, which is actually the portion of the direct common tangent between the two circles. Next we are going to see how to calculate the length of the transverse common tangent between the two circles. I'm going to do a little more construction here. I'm going to extend the PM line a little bit, and then I'm going to draw a line from Q onto this extended PM, which will be parallel to MN. And let's assume that the extended PM and the new line drawn from Q, they meet each other at point S. And from here, can we say that the quadrilateral MSQN is a rectangle? Because PM and QN, they are parallel, and I have extended PM up to S, and PM is perpendicular to MN. So this quadrilateral has opposite sides parallel and one angle 90 degree, and in fact all of those angles will be 90 degree angles. So we have a parallelogram with 90 degree angles. That means it is a rectangle. And from here we can say then MN will be equal to SQ, and also we can say that MS will be equal to NQ, which will be equal to R sub 2. Now PS is equal to PM plus MS, which is equal to R sub 1 plus R sub 2. Angle PSQ is equal to 90 degree. That means triangle PSQ is a right triangle. And if we use Pythagoras theorem on the right triangle, we can say PS squared plus SQ squared is equal to PQ squared. And from here we can say SQ squared is equal to PQ squared minus PS squared. And then we can say MN squared, in place of SQ we can write MN. So MN squared is equal to PQ squared minus R sub 1 plus R sub 2 whole squared. And from here we can say then Mn will be equal to the positive value of square root of PQ squared minus R sub 1 plus R sub 2 whole squared. So that is the length of the transverse common tangent between the two circles. I hope things are clear up to this point. Next, let's try to find the coordinates of the point D. We know D divides the PQ line segment externally in a ratio of R sub 1 is to R sub 2. So from there we can say then x sub 1, which is the x coordinate of the point D, will be equal to R sub 1 times negative G sub 2 minus R sub 2 times negative G sub 1 over R sub 1 minus R sub 2. Here I am simply using the section formula for external division. And if we simplify this, the quantity looks like G sub 1 times R sub 2 minus G sub 2 times R sub 1 over R sub 1 minus R sub 2. And similarly, what will be the y coordinate of the point D? Well, the value of the y coordinate will be like this. It will be f sub 1 times R sub 2 minus f sub 2 times R sub 1 over R sub 1 minus R sub 2. So what will be the length of the PD line segment? Well, that's pretty easy. We can use the distance formula. Using the distance formula, we can say then the length of PD will be equal to positive square root of x sub 1 minus negative G sub 1 whole square plus y sub 1 minus negative f sub 1 whole square, and that can be written as positive square root of x sub 1 plus G sub 1 whole square plus y sub 1 plus f sub 1 whole square. Next, let's try to find out the angle between the two direct common tangents. Let's assume that the angle ADP is theta. So the angle between the direct common tangents will be theta plus theta. That will be equal to 2 times theta. And what will be cosine of theta? Well, cosine of theta will be equal to AP over PD, and that can be written as R sub 1 over PD. And we have already calculated the length of PD, so we can easily calculate the value of cosine of theta. And from here we can say then theta will be equal to cosine inverse of R sub 1 over PD. And then what will be the value of 2 times theta? Well, that will be 2 times cosine inverse of R sub 1 over PD. So that is the angle between the direct common tangents. Next, we are going to try and find out the angle between the transverse common tangents. Let's assume that angle is 2 times alpha, and before we can calculate that, we need to calculate the coordinates of the point t. So let's quickly calculate the coordinates of the point t using the section formula. X sub 2 will be equal to negative of g sub 1 r sub 2 plus g sub 2 r sub 1 over r sub 1 plus r sub 2. I am simply using the section formula for internal division because t internally divides the PQ line segment in a ratio of r sub 1 is to r sub 2. So I am simply using the section formula to find the coordinates of the point t, because we already know the coordinates of the point P and point Q. So that is the x coordinate of the point t. Let's try to calculate the y coordinate of the point t. Using similar techniques, we can show that the y coordinate of the point t will be equal to negative of f sub 1 r sub 2 plus f sub 2 r sub 1 over r sub 1 plus r sub 2. There again we need to use the section formula for internal division. So now we know the x coordinate of the point t and y coordinate of the point t. So then we should be able to calculate the length of pt. The length of pt can be determined by using the distance formula, and that will be actually equal to square root of x sub 2 plus g sub 1 whole squared plus y sub 2 plus f sub 1 whole squared. Now what would be the angle between the transverse common tangents? Well, that will be equal to alpha plus alpha, that 2 times alpha. Now what will be sine of alpha? If we simply look at the triangle PMT, then sine of alpha can be written as PM over PT, which is equal to r sub 1 over PT. We know the value of r sub 1. We have just calculated the value of PT. So then we can easily calculate the value of sine of alpha. And from here we can say then alpha will be equal to sine inverse of r sub 1 over PT. That means 2 times alpha will be equal to 2 times sine inverse of r sub 1 over PT. So that is the angle between the transverse common tangents. I hope things are clear up to this point. Next, we are going to try and find the equation of the direct common tangents. Let's suppose the equation of the direct common tangents are like this: y minus y sub 1 is equal to m sub 1 times x minus x sub 1, and also the other one would be y minus y sub 1 is equal to m sub 2 times x minus x sub 1. As you can see, the slope of the two direct common tangents will be different. So I am indicating one slope to be m sub 1 and another one to be m sub 2. And both of them go through the point D, whose coordinates are x sub 1 comma y sub 1. We have already calculated the values of x sub 1 and y sub 1. So here the equations are going to be like this. Now what would be a common notation for these two equations? Well, if we simply assume the two values of m sub 1 and m sub 2 to be a combined value as m, eventually we will calculate the two possible values of m. But for now, let's assume that their slope is equal to m. Then we can write their equations as a combined equation like this, where m will have two values. So y minus y sub 1 is equal to m times x minus x sub 1. And from here, can we write it like this? Y minus y sub 1 is equal to m times x minus m times x sub 1. And from there, we can say then mx minus y plus y sub 1 minus mx sub 1 is equal to 0. So here we have the general equation of the two direct common tangents, assuming m will have two possible values. Now what is the distance of the AD line from P? Well, that distance is nothing but the radius of the larger circle, which is r sub 1. And now if we use the formula for the distance of a line from a given point, we can write that distance like this. I have already created a separate video on this topic. I have shared the link in the description. Feel free to watch that video. So I am simply using the formula for the distance of a line from a given point. And the coordinates of the given point P are of course negative g sub 1 comma negative f sub 1. So in place of x and y, I have used negative g sub 1 and negative f sub 1. And I am simply using that formula for the distance of a line from a given point. And from here we can say absolute value of this quantity will be equal to r sub 1 times square root of m squared plus 1. Now to get rid of the square root on the right hand side and to get rid of the absolute value sign on the left hand side, we can square both sides. And if we do that, our equation going to look like this. And we can rewrite it like this. And on the right hand side, we can write it as r sub 1 squared m squared plus r sub 1 squared. And if we expand the left hand side going to look like this. And the right hand side will be like this. And then if we bring everything to the left hand side, then our equation is going to look like this. And we can rewrite that like this. And if you carefully look at this equation, everything is pretty much known. The only unknown here is m. And this equation looks like a quadratic equation in m. G sub 1, x sub 1, r sub 1, f sub 1, y sub 1, they all are known quantities, right? So this equation has everything known, the only unknown is m, and it looks like a quadratic equation in m, and we're going to use the quadratic formula to find the values of m. And the two possible values of m can be written like this. I have simply used the quadratic formula. Let's assume that the value of m sub 1 can be obtained by using the plus sign, and the value of m sub 2 can be obtained by using the minus sign. So here we have the two possible values of m, and using the value of m sub 1, we are going to get the equation of the first direct common tangent, and that equation will look like this: y minus y sub 1 is equal to m sub 1 times x minus x sub 1. And similarly the other one will look like this: y minus y sub 1 is equal to m sub 2 times x minus x sub 1. So here we have the equations of the direct common tangents. Here you have seen the technique of how to calculate the two possible values of m, and then simply use that value in the equations. We have already calculated the values of x sub 1 and y sub 1, and just now we calculated the values of m sub 1 and m sub 2. So just plug in those values, then you have the equations of the two direct common tangents. Next, let's try to find the equations of the transverse common tangents. Here again, let's assume that the equations are like this: y minus y sub 2 is equal to m sub 1, the uppercase m of course, m sub 1 times x minus x sub 2, and also the other one would be y minus y sub 2 is equal to m sub 2 times x minus x sub 2. Here I am using the uppercase m to keep it different from the previous two equations that we just derived. Now we have already calculated the coordinates of the point t, so we know the values of x sub 2 and y sub 2. The only thing we have to somehow figure out would be the values of m sub 1 and m sub 2. And here again we are going to use the same technique as we just did. Let's write the equation as y minus y sub 2 is equal to uppercase m times x minus x sub 2, and then we are going to create an equation through which we will calculate the two possible values of m. We can write the right hand side as mx minus mx sub 2, and if we convert that into a form of ax plus by plus c equals 0, then our equation will look like this: mx minus y plus y sub 2 minus mx sub 2 is equal to 0. And then what will be the distance of KL from the point P? Well, that distance is the radius of the larger circle, which is r sub 1, and using the formula for the distance of a line from a given point, we can derive that as absolute value of m times negative g sub 1 minus negative f sub 1 plus y sub 2 minus mx sub 2 over square root of m squared plus negative 1 squared. Here the coordinates of the point P are actually negative g sub 1 comma negative f sub 1, and from here we will try to calculate the two values of m. Let's bring the denominator to the right hand side. So our equation will look like this, and then we are going to use the same technique as we practiced before. We'll square both sides and then we'll solve for the two values of m, and let's call them m sub 1 and m sub 2. It will be exact same technique. Just follow the same technique as we deployed for the slopes of the direct common tangents. We are going to use the same technique. You can use the same technique to find the two values of uppercase m, and then if we assume that the slopes are m sub 1 and m sub 2, then our equations for the transverse common tangents can be written like this. I hope it is clear to you how to find the equations of the direct common tangents and the transverse common tangents. Next, we are going to take an example. Let's suppose we have an example like this that says, for the two given circles, find the equations of the direct common tangents and the transverse common tangents and their lengths. The two equations of the circles are given as x squared plus y squared plus 4x minus 2y minus 4 equals 0 and x squared plus y squared minus 4x minus 6y plus 12 equals 0. So let's get started with the solution. If we compare the equation of the first circle with the general form, then we can say that 2 g sub 1 x is equal to 4x, and from here we can say g sub 1 is equal to 2 and negative g sub 1 will be equal to negative 2, and similarly 2 f sub 1 y will be equal to negative 2y, and from there f sub 1 is equal to negative 1 and negative f sub 1 is equal to 1. And if we calculate the radius of the first circle r sub 1, that turns out to be 3 unit. Similarly, we are going to compare the given equation of the second circle with the general form of the equation of a circle, and from there we can say that 2g sub 2x is equal to negative 4x. That means g sub 2 will be equal to negative 2 and negative g sub 2 will be equal to positive 2, and 2 f sub 2y is equal to negative 6y, and from there f sub 2 is equal to negative 3 and negative f sub 2 will be equal to positive 3. And if we calculate the radius of the second circle, it turns out to be 1 unit. Let's calculate the coordinates of the point of intersection of the direct common tangents. The x coordinate will be like this, and if we plug in the values, it's going to look like this, and if we simplify that, it turns out to be positive 4. Similarly, if we calculate the value of the y coordinate, that also turns out to be positive 4. So the coordinates of the point of intersection of the direct common tangents are 4, 4. Let's try to calculate the coordinates of the point of intersection of the transverse common tangents. There the x coordinate will look like this. It will be positive 1, and the y coordinate turns out to be positive 5/2. So the coordinates of the point of intersection of the two transverse common tangents would be 1, 5/2. And here I have made a summary note that the coordinates of D, which is the point of intersection of the direct common tangents, the coordinates are 4, 4, and the coordinates of T, which is the point of intersection of the transverse common tangents, that is 1, 5/2, and then coordinates of the center of the first circle would be negative 2, 1, and the coordinates of the center of the second circle would be 2, 3, radius of the first circle 3 unit, radius of the second circle 1 unit. So now we have all the information we need. Now coming up with the equation of the direct common tangents and the transverse common tangents will be really easy. So let's get started. Let's assume that the equation of the direct common tangents is like this: mx minus y minus 4m plus 4 equals 0. I have simply used the values of x sub 1 and y sub 1, which are nothing but the coordinates of the point D, and then I am using m as the unknown slope of the two direct common tangents, and we are going to find the two possible values of m. Distance of the direct common tangent from P will be equal to r sub 1, and using the formula for the distance of a line from a given point, we can say that absolute value of m times negative 2 minus 1 minus 4 times m plus 4 over square root of m squared plus negative 1 squared is equal to 3. 3 for the r sub 1, the radius of the first circle, that is 3 unit. And if we simplify that, our equation going to look like this. Next we are going to square both sides. Our equation looks like this, and next we are going to expand it. And you see there is a positive 9 on both sides, which will cancel out each other. So our equation is going to look like this, which is essentially like this: 27m squared minus 36m equals 0. And from here we can say that this is nothing but 3m squared minus 4m equals 0. We divided both sides of that equation by 9, so we get 3m squared minus 4m equals 0. And from there we can say that m times 3m minus 4 equals 0. And from there we have the two possible values of m, that m is equal to 0 or m is equal to positive 4/3. Now let's plug in this value in the first equation. So y minus y sub 1 is equal to m sub 1 times x minus x sub 1. Here I am using 0 for the value of m sub 1, and I am using 4 for x sub 1 and 4 for y sub 1. Those are the coordinates of the point D. And if we simplify this, our equation going to look like y minus 4 equals 0, and that is nothing but y equals 4, and that is the equation of the first direct common tangent. And what would be the equation of the second direct common tangent? That will be like this: y minus 4 equals 4/3 times x minus 4. That 4/3 is the value of m sub 2. I am using the second value of m that we just calculated. And if we simplify this, our equation going to look like that. And from there we can say that our equation will look like this. And from there we get 4x minus 3y minus 4 equals 0. That is the equation of the second direct common tangent. So we have been able to find the equations of the direct common tangents. Next, we are going to try and find the equations of the transverse common tangents. For the transverse common tangents, let's assume that the equation would be like this: y minus y sub 2 is equal to uppercase m times x minus x sub 2. Here y sub 2 and x sub 2, they are nothing but the coordinates of the point T, which is the point of intersection of the transverse common tangents. And if we simplify that, the general equation of the transverse common tangents will be like this: and the distance of the transverse common tangent from the first center would be equal to the radius of the first circle. And if we use the formula for the distance of a line from a given point, that distance will look like this, and that will be equal to the radius of the first circle, which is 3 unit. And if we bring the denominator to the right hand side, then the equation is going to look like this. and the right hand side essentially looks like this. If we bring that 4 from inside the square root, it will come out as a positive 2, so it will become 6 times square root of m squared plus 1, and then our equation going to look like this. If we simplify the left hand side little bit, it will be like absolute value of negative 6m plus 3, and the right hand side as before. And if we square the both sides, our equation looks like this. The right hand side essentially looks like this. And if we expand the left hand side, our entire equation going to look like this. And from here, if we bring everything to the left hand side, our equation is going to look like this. And here you see there is a very interesting observation. The coefficient of m squared term becomes 0, and that is very important. Please make a note of it, that the coefficient of m squared term becoming 0, that means from this equation we will be able to find only one value of m, but somehow we have to find the second value of m as well, right? So for now I am going to carry that coefficient of m squared term as 0. And if we take the remaining terms, which are negative 36m and negative 27, if we take these two terms, then our equation is going to look like this. And if we take that negative 1 as a common factor, then our equation is going to look like this. And because we know this was going to be a quadratic equation, there will be two linear factors. We have one linear factor which is 36m plus 27, and the other linear factor is looking like a negative 1. So I am going to represent that in form of an assumed linear factor. Let's say that assumed linear factor is a times m plus b, that is a linear factor, and we'll calculate the value of a and b. So from these two linear factors, we can say then a times m plus b should be equal to 0, or 36m plus 27 should be equal to 0. Next I am going to compare this a times m plus b with negative 1. And if we do that comparison, a seems to be 0 and b seems to be negative 1. So then we can write that one factor as 0 times m minus 1 equals 0, and the other factor is 36m equals negative 27. And from here we can say then 0 times m is equal to 1, and on the other side 36m is equal to negative 27. And from the first one we get m is equal to 1 over 0, even though it's an undefined operation, but I am writing it like this because we are talking about the slope of a line, and the slope is also a ratio, and this type of a value is possible. If you think about slope as tangent of theta, which is equal to sine of theta over cosine of theta, and this value is possible when theta is equal to 90 degree. That means if that line is a vertical line, then we could have a slope like this, 1 over 0, sine of 90 degree over cosine of 90 degree. So in this case, actually the slope is infinity. You can say undefined, but the slope is actually approaching infinity. And the other possible value would be negative 27 over 36, which is equal to negative 3 over 4. Next, I am going to plug in the two possible values of m one by one in the equations of the transverse common tangents. So if we transform this equation slightly, it can be written like this. And there I am going to plug in that crazy value of m. I am doing it just to show you how we derive the equation, right? Even though I know division by 0 is not allowed in mathematics, but in this case we are talking about the value of a slope which can be 1 over 0 when the angle of inclination is 90 degree, right? So from here we can write it like this, and that turns out to be 0. So you see how the y term kind of disappeared, and our equation is going to look like x equals 1. And x equals 1 is nothing but a vertical line going through the point 1, 0. So that is the equation of the first transverse common tangent, x equals 1. So whenever the square term disappears, you can assume that one possible value is actually approaching infinity. So one possible value would be infinity. So we are going to take m as infinity when the m squared term disappears. I hope it made sense. Next, we are going to use the other value of m to derive the second equation, and there I have plugged in the value as negative 3 over 4 for m, and if we simplify it, our equation is going to look like this: 3x plus 4y minus 13 equals 0. So those are the equations of the transverse common tangents. So one interesting thing that we learned here is when the m squared term disappears, we have to assume that the value of m is approaching infinity. And that happens when the angle of inclination is approaching 90 degree. This brings us to the end of this video. I hope everything made sense. Thank you for watching. See you in the next video.